Okay, so we're going to be dealing with our most complicated video yet. And this is, we're still just going to look and show it's a linear transformation. We're going to show how to compute what T alpha beta is, or the matrix representation of T using alpha beta is, and a few more examples. But we're looking now with the real 2 by 2 matrices to the real polynomials of degree at most 2. And T, when you look at the transformation applied to A, it's the trace of A plus the 1/2 entry times X plus the 2 1/3 entry times X squared. First, we want to show that this is a linear transformation. But in order to do this, there's a few things that we need to do. We need to understand what the trace of A is. We need to understand what the first second entry of A is and the second first entry of A is. And then from there, we need to apply this equation to each of these basis vectors, represent them using these basis vectors. It's going to be a long, drawn-out process. But if you're able to look at this and go, oh, I know how to do this. This isn't that scary. You really know these 5 different ideas, which is exactly the point of these videos. Get you from, I don't know what's going on, to I really know what's going on. So here we want to let V1 equal A1, B1, C1, D1. So we have one matrix, and V2 equaling A2, V2, or A2, B2, C2, D2. And then we're going to look at E and F being in my field. So we have 2 matrices and E and F in our field, and we want to look at the left-hand side equaling T of E V1 plus F V2, and the right-hand side is going to be ET of V1 plus, or E1T V1 plus E2T V2. So here for the left-hand side, we get T of E A1 B1 C1 D1 plus F A2 B2 C2 D2. And this is equal to T of, and if I apply the multiplication and addition, it's EA1 plus FA2 EB1 plus FB2 EC1 plus FC2 and ED1 plus FD2. Now we need to apply our equation. And the first thing we need to know, what is the trace? The trace of A, also given by TR of A, equals the sum of the diagonal entries, or AII. So in our case, if we have A, B, C, D, the trace of this matrix is going to be A plus D. So the trace of our matrix is going to be EA1 plus FA2 plus ED1 plus FD2. And now we're going to add A12 is the first row, second column. So it's going to be EB1 plus FB2 times X. And then the tooth 1 entry is this entry over here. So it's going to be C1 plus FC2 times X squared. Right? So that's our equation. And we'd like to show that the right-hand side is equal to that. And like we did last time, while we set it up so we have right-hand side, left-hand side, we're going to take this right-hand side and we're going to move it below our analysis for the left-hand side and expand and show that they're equal. And once again, we're going to create some space. And we're going to apply the definition. So this here is equal to ET of A1, B1, C1, D1 plus FT of A2, B2, C2, D2, which is equal to E A1 plus D1 plus B1X plus C1X squared plus F times all of, and remember, E is times the entire output, F is times the entire output, A2 plus D2 plus B2X plus C2X squared. Expanding, we get EA1 plus ED1 plus EB1X plus EC1X squared plus FA2 plus FD2 plus FB2X plus FC2X. Grouping and rearranging, we get EA1 plus FA2 plus ED1 plus FB2 plus EB1 plus FB2 times X plus EC1 plus FC2 times X squared. And again, there's a lot of manipulation that we did that we would then reference if we were to be doing a rigorous proof. But at this point, there's so much that we need to do that we might start not justifying every single step. So in these cases, it's always nice to justify every step. But here we really want to see, okay, you can really prove left side equals right side. And you know what we're trying to show. But here we now can conclude that therefore left-hand side equals right-hand side. So T is a linear transformation. We have a nice linear transformation. And again, these videos aren't intended to show you how to answer these rigorously, but the process involved to get to the right answer. Now we want to compute what T is in terms of alpha, beta. So we're going to be looking at T applied to each of the input out vectors and then represent them using each of our beta bases. So our first vector is what's going to happen to T of 1, 1, 1, 1. Well, this equals 1 plus 1, or the trace, plus 1, plus 1x plus 1x squared, which equals 2 plus x squared. We want to know what this is in terms of a times 1 plus 2x plus 3x squared plus b times x plus x 2x squared plus c times x squared. I'm just going to verify, yeah, I do have the right basis vectors. So this gives me the system of equations A equaling 2, B plus 2A equaling 1, and let's just rewrite these in the order. 2A plus B equaling 1, and 3A plus 2b plus c equaling 1. Now we could create a system of equations if we wanted to, or we can do a substitution argument. So we can plug a into our second equation to give us 2 times 2 plus b equals 1, implies that b equals minus 3. And now plugging in here, 3 times 2 plus 2 times minus 3 plus c equals 1 implies that c equals 1. So we can create the system of equations, or we can just use substitution to solve. Well, this gives us the coordinates vector that, or this gives us that a, b, and c is equal to 2 minus 3, 1. Now what about t of 1, 2, 1, 1? This is going to equal 2 plus 2x plus 1. So, and this is going to be equal to a 1 plus 2x plus 3x squared plus b x plus x squared plus c x squared. So this gives us the system of equations. A equals 2, 2a plus b equals 2, and 3a plus 2b plus c equals 1. Should be 1x squared. Again, using a substitution argument, we get that 2 times 2 plus b equals 2, which implies that b equals minus 2. And now 2 times 3 plus 2 times minus 2 plus c equals 1 implies that c is equal to 6 minus 4 is 2. Bring the 2 over, c equals minus 1. So now a, b, c is going to equal the vector 2 minus 2 minus 1. We'll carry on in a similar way to look at what happens to t of 1, 1, 2, 1. This here is going to be 2 plus 1x plus 2x squared. And again, we set it equal to a 1 plus 2x plus 3x squared plus b x plus x squared, 2x squared. And let's fix this up here as well. This should be x plus 2x squared. Here we have x plus 2x squared plus cx squared. Well, this gives us the system of equations that a equals 2, 2a plus b equals 1, 3a plus 2b plus c equals 2. And plugging in here, we get that 2 times 2 plus b equals 1, implies that b equals minus 3. From here, we plug in 3 times 2 plus 2 times minus 3 plus c equals 2, which implies that c equals 2. So our solution vector a, b, c is going to be equal to 2 minus 3, 2.